to talk about not using CUDA. Thank you.
Hi, I'm Dave Airlie. I work at Red Hat in Brisbane. Mostly working on graphic cards situations for the last few years. You might have seen me talk. But I've recently started getting a bit more involved in compute and CUDA, that sort of area of the world, but not directly in CUDA, because CUDA, as everyone in here would know, is a binary-only closed source stack that has no interest to me, and it's very hard for me to recommend that anyone could use it. But what else can they use? So my talk today is about I don't want to use CUDA. Someone can work out what movie that was a reference to. It's something my kids watched a lot when I wrote the title of this slide. I'll tell you at the end. If I don't, remind me. But yeah, just to give you an overview of what I'm going to talk about today. So I'm going to start off with just some sort of use cases. What's this being used for in the world at the moment? I'm going to move on to then what sort of APIs exist to solve those use cases and what their status is. And then what is a compute stack? What are the pieces of a graphics card, GPU compute stack that I'm talking about here? How those stacks and those APIs fit together? How they're developed, how they're packaged. And then a bit more of a speculative, this is what I kind of like to see happen in the future. You know, what way could this end up? So we'll start with use cases. So the main use cases I hear about and I see from, in the industry generally circle around these sort of areas. You've got a lot of interest in the AI/ML areas, particularly around the whole TensorFlow system. TensorFlow then is built on top of a couple of other little things like Eigen and BLAST sort of areas. So you got a lot of BLAST as a linear algebra software. So that's one of the areas that we see quite a interest at the moment in. I'll go into a little bit more where I think it's going to go. HPC then is like high performance computing. You see a lot of that. It's usually massive supercomputers and very specific work sets. The code is written on top of CUDA, but there's a very specific set of code that's just for that task. And then scientific, non-massive computing and non-AI/ML mostly sort of falls into the scientific area. It's like people have data sets, they want to process them. They're not doing it on massive clusters. They're not doing it with AI/ML, but they've got their own sort of processing algorithms and stuff they want to run. So these are the sort of areas you generally see CUDA being used. It turns up in other places, but you'll get embedded. You'll get a bit of other. But these are the main ones I'm seeing at the moment. So what is CUDA? Well, it's an API. It's defined by NVIDIA. There is no CUDA standardization body. There's no CUDA standard. There's just whatever NVIDIA decides is the next graphics chip is going to have, that's the next version of CUDA usually. Or if they have new features, they just make a new version of CUDA. It's all closed source. There is open source re-implementations of some parts of the stack, but generally I think you can get an alternate compiler. But generally, it's all closed source, all controlled by NVIDIA. It's C++ based single source. I'll go into a little bit later what that actually means. But the idea is you write software and the control flow is single source. The source, you don't know where the source is going to run on the graphics card or the CPU. They're not separated. They're all in one source file. You can read through it, track where the control flow goes, and then when it's compiled, it decides where it ends up. And then there's a bunch of support libraries that NVIDIA produced to support CUDA. So they've got CUDNN, which is used a lot with TensorFlow. They've got BLAST implementations, and they've got a number of other things that they produce. It's definitely the top of the leader. But what's out there that's sort of up and coming, or what's challenging it? AMD have defined, again, I don't think it's standard. It might be a standard. They set up a standards body for it, but I don't know who else is actually putting stuff into that at the moment. Everyone's in it, but I'm not in it, so I don't know what's happening inside it. It's HIP, which stands for just rolls off the tongue here, Heterogeneous Compute Interface for Portability. Yeah, I had to write it down. I couldn't remember that. The source code of this does exist. It's released on GitHub. Again, HIP itself is a C++-based single source language. And they have a bunch of support libraries in the same model. So it's kind of like, I can't believe it's not CUDA in a lot of ways. But they've done most of it, but then they've actually released the source code to it. Again, that's something I'll get into a little bit further on later. Another thing you often hear is, oh, OpenCL is this competitor to CUDA. That's what we should be using in open source. Why aren't we using OpenCL to do all of these fancy things? OpenCL is a Khronos standard, which means it's a standard defined by the Khronos group, which does OpenGL and Vulkan and those standards. All of the big graphic card companies are members. Red Hat's a member. There's a number of implementations of this from different graphics vendors. OpenCL has kind of got this bit of a weird, they brought out the 1.2 standard. Everyone started implemented that, and then they brought out these 2.0, 2.1, 2.2, and NVIDIA kind of went, we'll just stick to 1.2, and that's kind of flatlined its pickup, because even if NVIDIA start bringing out 2 and later on, everyone was like, oh, well, that's what we're going to compete against. They're running it on the same graphics card. They're running the NVIDIA stack. It's like, so it's kind of been hobbled a little bit. But one big difference between this and the previous two that actually sort of answers the question, why can't we do these things with OpenCL, is it's not single source. So when you write an OpenCL program, you write a chunk of C or a chunk of C++ that's going to run on the graphics card, and you run your chunk of C or C++ that's going to run on your host, and there's just like kernel launching APIs to launch those kernels on the graphics card. So you can't see that sort of control flow, the data flow as easily, because it's like having to hop across and go through this code, and it's just a different concept. And a lot of the pieces of especially the TensorFlow stack and the Eigen stack are very sort of C++ single source. They're very template heavy, and originally OpenCL didn't even have C++ support. So that's another thing that's sort of happening. I don't think that's picking up too much, but maybe we'll get some support for it. But yeah, the big difference with OpenCL is this: it's not single source, and there wasn't C++ support until recently. Also, it has online and offline compilation. So generally with CUDA, you do all the building, you get an object, a binary out at the end. When you run that, that might get optimized a bit, but that gets executed. With OpenCL, you have the C code, the OpenCL C code in the binary, and when you run it, it compiles it then. So it actually parses all the C code and runs it through a full compiler at that stage when you're actually executing it for the first time. It may cache some of that or it may do things, but that's online. You can, with later versions, do offline, where you can actually run it through in advance, get a binary back, and then give it back that binary later. But it's a bit messier. It's a bit more like distribution. You don't have this single executable with everything in it. But a new feature that's been added to OpenCL as well is this thing called SPIR-V. Again, another segue later will tell you what IR is, but they've realized that was a problem. Having either just a big chunk of source or a big chunk of random binary, people don't really want to distribute that. You don't want to be leaving your fully annotated C source inside the binaries you're giving to people, apparently. Don't know why. That seems insane. Like, perfectly exactly what you want to do. But they decided to have an intermediate representation. They compile the C code down into this other binary that's not quite the finished work, and then they'll finalize that, which is just compile it, but they call it finalization to distinguish it from the other stage of compilation, just to keep everything, So they're sort of like what's been going on up until recently. Recently, a newer, if I can figure out which button push, a newer sort of standard has sprung up, which is, it's only recent. I haven't got the dates in my head, but the final versions of the standard haven't been out that long. Again, this is called SYCL, if you want to pronounce it. I think that is the correct pronunciation, SYCL. It's a Khronos standard again, but it's C++ single source. So it's solving that. I want one program. I want to be able to write the code in one thing and then have it easy to understand, and it will just run where it's applicable, where it needs to. If it needs to execute the GPU, it will do that. Generally, what this was done, if you want to launch on the CPU side, there's no graphics chip, it'll use something like OpenMP. But if you have a graphics chip, it will use the OpenCL interface to actually launch the kernels. Again, the things it's going to launch will either be that SPIR-V or they'll be binaries. Okay, I'll get into where the differences are at that in a bit. Implementations of this so far, most of this was driven by a company called CodePlay. They've got a closed implementation of this. They're pretty big in the standards committee. Excuse me. I've been working with Xilinx and Red Hat on this thing called Tricycle, which was like an open source runtime and trying to get the compiler stuff ready. So it's pretty much been more of an educational exercise in figuring out how all this stuff fits together. But then I gave this talk I'm going to say verbatim, but no, this bit changed. But I gave this talk about 3 months ago in Vancouver at Plumbers Conference. And in between then and now, last week, Intel have come out and say on the CLang list and said, we really want to upstream our CLang port of SYCL and our runtime of SYCL. And then it's like, can we help? And I said, what can we do? So they're currently waiting on just getting it onto GitHub first, but this looks like a pretty big chunk of the puzzle actually going to arrive in the next few weeks. It'll probably take a bit of time to upstream, but they seem to be committed to that, and they've asked me about helping out, and if the guys at Xilinx are going to talk to as well. So this was a big change, and it may bring things on quite quickly. Other things in the area, there was a C++ AMP standard. This is a Microsoft standard. I haven't really looked too deeply into it. I think there's some bits of it around in, I think AMD had stacks for pieces of it. There's OpenMP. OpenMP is like the CPU parallelization thing. It's getting better for GPUs, but people keep saying, oh, you should just use OpenMP. But they're generally people who work on CPUs and don't actually understand that that doesn't really work on GPUs. That the sort of threading you need isn't the sort of thing that OpenMP really gives you yet. The OpenMP people are working on this as well, though. The problem is everyone is working on it. That's the question of what's going to actually happen. There was OpenACC. Again, that's another similar vein to OpenMP. NVIDIA work on that a bit. There's a GCC code for it. I haven't looked into that lately too much. And there's also this kind of outlier. So the Vulkan API arrived that I talked about previously, and someone has talked about this week. But Vulkan has the ability to launch compute shaders. And it's a very low-level API. The problem is the compute shaders it launches are not the same thing as the compute shaders that OpenCL launches. They're quite different beasts. They can both be implemented as SPIR-V, but when you get down to what they actually do, they run quite differently. But, for example, Vulkan didn't have pointers. So that's kind of a feature people wanted. But Vulkan just got pointers in an extension, and that just made a whole lot of problems way easier. So the approach to how the standardization is going is quite different with Vulkan. They pretty much want good, solid features, and they want them with implementations. They don't want people saying, this is a great feature, we should put it in the standard, and then 2 years later, no one's implemented it. That's bad. But again, where is this sort of going, really? The future is C++, something in 20. That could be actually very good. I'll have 2 question marks there. It could be 30. Who knows? Hopefully 20. But there's a lot of push from all of these groups involved to get a C++ standard. This should just be part of the language. Why are we all implementing these layers on top? So there is ISO standards body work going on. Everyone is inputting. The SYCL people are inputting, the ACC people, the MP people. Everyone's putting in their work. I'm not actually on that standards body. I could be, but I don't think I want to. But it's quite, there's ongoing work. Someone from Red Hat works on it, and it still meetings happen quite often, and they discuss it. But one thing they've kind of realized, at least at this point with the C++ standards, was there's no point just, again, writing a standard without actually validating that it's useful. And so that's what a lot of these other implementations are for. It's like, well, this is the way we think it should work, and here's our implementation of how it should work. Could we get that in the standard, or we take bits from other places? So it's trying to converge all the existing implementations into one single C++ standard. And even if you have that, that's just your programming language. You still need something to run it on. And so you still need a runtime, you still need all these other things, and that's sort of like, well, we're going to have to build those parts of the stack anyway. There's no point sitting around waiting for the C++ standard to finish and then go, now we'll start doing it, because there's a load of work you need to do anyway. So we may as well start moving it forward in some way. So that's kind of just the overview. That's where things are sort of at the moment. But to sort of take it into the next, what are the pieces of this? How does the stack look? So this is kind of a generic picture of a compute stack. It's not mostly a sort of a single source compute stack, but you pretty much at the top, you've got your application source. You feed it into your compiler. Compiler looks at it and goes, okay, this chunk of code is going to go on the host. This chunk of code is going to go on the device. It'll compile both of those. So generally, it parses all the C++ into AST, and then it figures out which bits go where. It converts all the host code into native object code. It converts all the device compile code into IR or binary, so intermediate representation or a binary. I'll get into that again. The IR is what you kind of like binaries are a bit messy, but I'll talk about that. And then it spits out an elf object file, and that's your executable, and that's what you want to run. What's inside your elf object file? 2 pieces, a CPU chunk of code and a chunk of GPU executable code, or code that you want to give to the GPU at runtime. Yeah, again, IR is what's out of in there. It can be binary as well. And then you got the other stage. Well, I've got this. How do I run it? Well, you launch it, but you have to launch it on top of some sort of runtime stack. And the runtime stack generally has a few support libraries, a bit of a runtime stack, the kernel driver for your graphics card, and then the hardware. So it's not hugely complicated, but I am making it a little bit easier. OpenCL is kind of different because of that online, offline sort of problem. It allows both. So when you actually go to run an OpenCL application, you may need to have a full OpenCL compiler in there to do all the compilation from OpenCL down to the stuff that you give to the runtime. So you may then have another IR compiler to do, and then you may run that on the kernel. So it's kind of like, yeah, the offline bit's the same. It's just pretty much a support library, OpenCL runtime, and the kernel driver. But if you go online, you've got a full compiler, like a full C++ or C compiler. That's not small, and it's like not fast generally either. So just a little bit of diversion, because I keep saying IR without really telling you what an IR is, but I think you now know enough that I can tell you what it is. Intermediate representations are a compiler world thing, but pretty much you have a high-level source language, and you've got low-level binary. And anywhere in between those, you're going to have representations of your code. These representations are called intermediate representations because they're between the two. And you're always converting from one down to the final one. Some compilers could have 2 or 3 of these. In the Mesa stack, I think there could be places you could go through 4 of those text programs. So they all have different places in the stack. Some are needed, some are better for transporting across the wire, some are better at compiling, some are better at compiling with low memory. But a few examples. So in this sort of compute stack, you generally see, you hear about NVIDIA PTX. So NVIDIA have a low-level binary format they call SAS. But they don't show you that. They don't document that. They don't tell you about that. There are people who reverse engineer it, but NVIDIA are not interested in revealing it. So what their compiler spits out when you build with CUDA is generally a binary with a big lump of PTX and a few SAS binaries beside it. So if they get onto a graphics card that they hadn't seen before of a new one, they can optimize the PTX, and the program will execute, and it may not be optimal. You should go back and rebuild, but at least it will run. PTX is like a low-level assembly, but they can translate that then to the actual assembly. AMD have their GCN. That's pretty much their ISA, and it's a binary. They don't really have an IR in their stack. They always give you the binary in the thing. They give you like 2 or 3 different binaries because it's different graphics cards. You need a different binary, but in their HIP stack, there's no real IR. You just get the binary. Khronos then defined SPIR-V. SPIR-V is an IR it's defined pretty well. It's a binary. It's SSA. It's sort of high level if you know anything about compilers. It's a pretty high level IR. And it's got 2 variants. People say, oh, it's SPIR-V. It should be able to run it. But no, OpenCL and Vulkan and GL now have, well, actually, the Vulkan GL is a bit mostly similar, but the OpenCL and Vulkan are very different beasts. You can use the same tools just to look at it, but in terms of executing it, they need a lot different resources and a lot different systems. There's quite a, so when you say SPIR-V, that's not really meaningful enough. You need to say SPIR-V with kernel for OpenCL or SPIR-V for shader for Vulkan. And then you have these are the IRs that you sort of see in the compute stack. You also have IRs hidden inside the compute stack. So in Mesa's case, the Mesa driver stack, we've got this thing called NIR, which is an internal intermediate representation. And we've also got LLVM IR you'll see used inside an LLVM, the stuff between tools. Oh, excuse me. So that's just sort of what IRs. They're an artifact of the compiler stack, but sometimes we want to see them out of the compiler stack, and that's what the first 4 are. So just on OpenCL Stacks, so I've gone through what a stack. We have a lot of OpenCL stacks. Some vendors have a lot of OpenCL stacks on their own. They don't need us to help. But the main ones we're starting to see sort of converge on. AMD have two, but they've got one based on their ROCm stack and one on their PAL stack, they call them. But they're kind of converging on the ROCm thing. But so, first thing is it's vendor specific. There's no way you're going to get this code to be ported somewhere else. NVIDIA then have their own OpenCL stack, which is all binary. And then Intel have recently announced their own OpenCL stack, which is Neo. So this is what the vendor OpenCL stacks look like. They all generally fork LLVM at some point. So they all contain a big chunk of LLVM, probably a big chunk of CLang. So there's complicated. Everyone has their own. I think it's pretty much the message we have to get across here. So how does the picture I showed you earlier of what a generic stack looks like? Well, this is what it looks like for the CUDA stack. It's pretty much CUDA application source, CUDA compiler, device compiler. It sticks NVIDIA PTX is the IR that comes for the device, and native object code sticks them in the alpha object file. So it's just that's what a CUDA stack generally looks like, a simplified version. And in execution, it's got CUDA libraries, CUDA runtime, CUDA driver, NVIDIA hardware. All of the above are generally binary. You may get some of the libraries open source. AMD have their ROCm stack. It's so that you can write CUDA code, run it through this thing called HIP, which translates it, and it translates it to their HIP code, and then you compile the HIP code, and it goes into the device compiler, and then produces AMD-specific binary code that goes into the ELF object file. So the big sort of step here is if you're compiling CUDA here, you pass it through HIP, and it searches and replaces all the CUDAs to HIPs in other places, and a few other things like that. But yeah, it's there's a lot of said. It's probably Perl or something, but yeah. And then when you execute it, you got the language runtime, ROCm runtime, ROCm sort of thunk layer where they can run it on different drivers, and the kernel driver, and then they've got the AMD hardware. So this stack is pretty much completely open source. Oh, sorry, completely sources. The license it's under is open source. I'll give you my distinction in a minute. And then we've got the Intel stack. So the Intel current stack is just OpenCL. They don't have a CUDA implementation that sits on top of this. They don't have HIP implementation. They do support SPIR-V as an execution. So it's not quite in the same category as the other two. The other two are pretty much focused on trying to get CUDA running with OpenCL as an extra. Intel have gone with OpenCL, and I think are trying to figure out what to do next with CUDA type situation. But then we have this OpenStack that sits in the Mesa tree that kind of got half written by AMD before they changed direction one time, and then other people kind of threw a few bits into it, and so on. But no one's really sat down and driven this thing. It's just been, we need this. People are doing educational work where you're just playing around trying to add things to it. So it's only doing OpenCL 1.1. I think the only thing missing from 1.2 is probably printf. But when you think about printf on a GPU, it's kind of hard. So it's not trivial, put it that way. So it's not, we can port it from somewhere else, so just no one has bothered yet. But it's based on the Gallium drivers that we use for all of our OpenGL stuff. So it's like we already have drivers for the hardware that can execute pieces of code, and we use those for all the accelerated graphics work. Well, why aren't we using those? And there's support for some AMD. Nouveau is getting support for more features of it. Free Adreno hardware, so the Adrenos, the Qualcomm hardware. But we also had this bit of a realization is like, well, we're going to see a few more ARM accelerator chips. They all want OpenCL as well. Running out our own stack for all these is going to get pretty, sad pretty quick. It's going to get very messy. Oh, excuse me. So that sort of gives you an overview of where we're at. Mesa needs work, but a lot of the pieces are there. And it brings me now to what we call, what do these vendors say when they open source something? NVIDIA are easy. NVIDIA never open source. They don't even like to use the word. They've got their binary. You know where you live. You're not getting great support because you can't figure out what anything does. But AMD have come out and said, oh, well, we've got our ROCm stack. It's open source. And Intel will come out and say our Neo OpenCL stack is open source. And I can't argue with that under the license. They are open source. But in terms of development model, it's very hard to do anything with. They're taking open source as a release model, not a development model, which we all know that the benefits of open source are the development model, not really the release model. It's like how you develop things produces the better results, not the fact that everyone can just get the source. Maybe we didn't know that all the time, but we all know it now. And so they also tend to exert control. It seems to be a big point that the first question you ask someone when they produce a new stack is, will you support us porting that to your vendor's hardware, your competitor's hardware? And they're like, yeah, no. Or will you take our patches back upstream to support that? Yeah, no. So you go around the vendors and you ask the same question of each one of them, the first question you ask in the hour-long meeting, and then you just don't listen for the rest of the hour-long meeting because they have answered the only question that matters. You have no way to involve yourself in the development process. Yes, you probably could submit bug patch fixes, but in terms of like feature adds or getting an insight into road mapping or getting an insight into where this thing's going, it's just not there. It makes it hard as a distro vendor, which I ostensibly am, to figure out how to put these in your distro, because how do I know it's not going to just regress every time I get a piece of code thrown over the wall on GitHub every 3 months? How do I validate that all this stuff is just, they're not just redesigning it internally without telling me, and 6 months later it's all going to be a new stack. It's like trusting yourself to this. It's like, oh, well, we see how Linux worked, and we'll just ignore that lesson and do it all ourselves. It's like they're not taking the lesson of how, and all these companies do contribute to Linux, and in some places they contribute to user space stacks collaboratively, but other parts of the company still haven't learned those lessons. All they heard was open source, and then that just means we put the source on GitHub, doesn't it? They didn't hear no, you have to work with your competitors, you need to build on a stack. A single thing is a much easier thing for a distro to package, much easier thing to get in front of your customers, much easier thing for support, much easier thing to build tools around. How do I build a debugger for this? Oh, well, I've got a CUDA debugger. Oh, well, I want to use ROCm. Oh, well, here's a whole new stack with a whole new debugger and a whole new interface. It's like, they're still not on the right path on the road. So it's, and then from a distributor, even if I was going to accept this, which I'm not actually in charge of this decision. I get input to it, but these are very large bodies of code. There's very little common code, and there's this. Everybody forks LLVM and CLang on a different day, and has their own stack of patches on top. Now, one of my tasks previously at Red Hat was maintaining our LLVM packaging for Fedora and RHEL, just so we could use it in the graphics drivers. And this was quite a sink of time just maintaining one fork of LLVM and CLang. I can't imagine, I probably could find the time, I can't imagine having the sanity after it to do this 3 or 4 times a month or a year. It's just having to collate these rapidly diverging forks of LLVM and CLang into one coherent place, or even just managing 4 of them and trying to figure out how shared libraries work. Because if you accidentally load the wrong LLVM, one application opens both stacks and they both get chunks of LLVM and CLang and they both have symbol versioning around the same time, that's not going to end well. But these aren't problems that the vendors see because they only care about their stack, and they would never contemplate that anyone would ever want to run software across different graphics cards. That's not in their, it's like, no, you just buy our graphics card. Why would you ever want to have a choice? It's like, doesn't come into their design decisions. So I've sort of decided, well, I'm just going to see what's out there now, and what can I propose as a sort of a stack. So what's my vision of what this should look like? Well, first of all, I think we need at least a reference implementation of something. It doesn't have to be the fastest thing. It doesn't have to wipe NVIDIA's CUDA off the map. It just has to be a solid reference implementation that's vendor neutral. So the same code, we can run it on the same, as much of it as possible shared across all of the devices. So, you could build something on your computer and take the graphics card out and put a different graphics card in, it still runs. Whoa, scary decision, This mightn't matter if you're a HPC, because you're unlikely to swap out all the graphics cards in a HPC overnight, but to get this sort of technology out in front of people and make it useful for actual, hackers, and just in that case, you need something that's a bit more, you can hand binaries to other people, or you can hand the source to other people, and it should work. So it needs to be based on a shared code base. There needs to be one sort of, maybe not one overarching project, but if you have a CLang contribution, it should be in CLang. It should not be a fork of it. If there's an LLVM chunk, it should be in LLVM. If runtime libraries, they should have a home somewhere, either in LLVM or in the free desktop sort of area. But it should be standards-based. CUDA, as great as some people tell you it is only great as long as it does what you want, but you can't get any input into that. The ability, standards-based things are generally slower to happen, which is why SYCL is only happening now. But generally, they're a better thing to base your future on because they're less likely to go rapidly away or diverge into something you can't get support for. But yeah, I'd like to have a common API at the top for running applications. So the runtime API will be common as much as possible. And the IR that we use inside the ELF will be common. So that, yes, you could include other things in there, but at least the base IR is something that can be executed across all of the vendors we have. And then I'd like to be able to enable common tooling. Maybe GDB isn't the greatest debugger for this sort of task, but if someone wants to make GDB work with this, it should work by plugging into the stack across all three vendors. It shouldn't be, I have to port it to all these different APIs and work out how they all work. Like, they may have to figure out how debugging works at all in the first place, but when they're finished, there should be one GDB that everyone knows how to use. So it seems fairly reasonable, to me anyway. So this is the kind of where I ended up, a proposed stack. It's the same picture from earlier, but with all of the pieces that are other people's replaced by pieces that are ours. Its source code would be C++ with SYCL, because SYCL is an actual standard. Even joining Khronos isn't simple, but it's at least a standards body with then people who care. The CLang, we'd have a single CLang SYCL front end. We would then have the LLVM-based device compiler come out of that, and that would produce the SPIR-V IR. And we would put the SPIR-V IR into the alpha object file along with the native object code. And then for the runtime piece, we would have the application, some SYCL libraries, a SYCL runtime based on the Mesa stack that would take the SPIR-V code and finalize it into whatever vendor's GPU you're running on's binary format that would again get executed by the GPU. So the idea would be that the SPIR-V code would run under OpenCL, and it would just execute it, and that would be the same across all the binaries. And the driver would be all a Mesa-based system, all with the Gallium drivers. There is an option to do this on top of Vulkan. Currently, it won't work, but I see Vulkan being where we actually wanted to go. OpenCL just seems like a stepping stone towards the Vulkan API is a lot better for this sort of thing than OpenCL is, but the Vulkan implementation of SPIR-V just doesn't have all the features yet. But since it just got pointers, and that was the big missing piece, things are starting to converge, and I suspect it may get there. I think we'll do the OpenCL thing first, and then worry about adding that on as a nice feature. So the idea then of the runtime would be based on Clover, which is the Mesa Stacks OpenCL runtime. We'd minimize the GPU-specific code as much, like abstract it out. We'd use the low-level Gallium drivers we have already. We'd use the same SPIR-V parser we have right now. We'd use near intermediate representation down to the hardware. Some driver backends might want to use an LLVM finalizer, which like the AMD code currently always does near to binary via LLVM compilation. Again, but that would be more of an implementation detail inside. It's not something you would be worrying about from a bigger picture. But one thing that just happened, as I said, that thing that's just happened a couple of weeks ago, and we'll hopefully actually get open source soon, and we'll endeavor to upstream, is pretty much this slide. Intel's plan to actually work with the community of people to do this pretty much covers this. So when I gave this talk 2-3 months ago, I was just facing into doing this. And now I don't have to, so this is good. Or at least I'm now facing into a different task of helping someone else's code get upstream, which I'm actually better at than doing it from scratch. So it works out well for everyone. This stack, the runtime pieces, we have most of this in various places. This is like, so for a while we had Gallium drivers for just the AMD and just the NVIDIA. And now Intel have started working on a Gallium driver and are going to produce it. So we will then have the low-level executing driver for all 3 vendors in one place. Another few people in Red Hat have been working on getting SPIR-V executable on top of Nouveau so that they can get the HMM feature in the kernel an actual open source user so that we don't get it removed from the kernel. And that's pushing ahead quite well. They've got that, basic examples working and running at that at the moment. So that the idea that you can execute a cycle or a SPIR-V kernel on an NVIDIA machine. And when I started playing with this about 6 months ago, the first task I did was get a SPIR-V kernel executing on my AMD card. So the pieces are all sort of slowly coming together in the Mesa side from just pieces from Intel. We just have to get the dots joined and get them sort of like solidified, and then optimization and all that will abound afterwards. But so in terms of where this is actually happening, it's a lot further ahead than it was when I first talked about it 2 or 3 months ago. It's probably not far enough ahead for anyone to actually use it yet, which is unfortunate because the whole point of the talk is, can I not use CUDA? You can though take, if you want another binary stack to use and want to use SYCL, you can just use the code play stack, but yeah, you're just digging a different hole, but it's at least a hole you have a better path out of because we have a path to get out of this with eventually for SYCL. So, but yeah, I encourage people that are into CUDA and have used CUDA or have people that use CUDA in their office to spread the SYCL sort of thing, get them to look at it, get them to sort of tell us what's wrong with it or where they need changes. I'm slowly learning C++ to actually understand a lot of this. That's actually been a bigger chunk of my time than anything else. So yeah, that's pretty much my talk. If anyone has any questions. Yeah. No? All right, microphone.
Hello, great talk. Are you aware of any modern VK-like initiatives for SYCL or OpenCL?
Yeah, well, question about Molten VK, which is to run stuff on Apple, just to clarify. So this is a layer that's been worked for Vulkan to run Vulkan apps on top of Metal, the Apple thing. There has been some talk of doing a SPIR-V execution on top of Molten, but again, Vulkan, because it doesn't have the missing pieces, I haven't done an analysis of what Metal has. I'm not sure if Metal compute shaders are actually capable of doing, again, all the features we'd need. So I suspect someone is looking at it, but I don't know how far it's being gotten to.
FPGA vendors, some of the FPGA vendors also use OpenCL to HDL compilers. Will that be able to somehow fit into this Mesa stuff as well, or is it completely orthogonal stuff? Kind of orthogonal, but it's kind of, so I've been working with Xilinx on this already for the last 3 or 4 months on and off. So Xilinx have a couple of engineers very interested in SYCL as well, and they're looking for it to run SYCL applications. They are unsure whether SPIR-V can actually do what they need, but I'm trying to encourage them to get SPIR-V enhancements done so that they can stop doing what they're doing, which is passing random LLVM IR, which changes every compiler and isn't stable, to give as their interface to their last stage compiler. But that, yeah, so the theory then would be that we could at least share the upper stack, and then the execution environment's a bit trickier because you have to do the HDL, and that's something that those people seem to like to not tell us about. But if someone wants to do that, I think there was a talk earlier from Tim about doing open source FPGA stuff, so maybe there's a space there to do something independent of the vendors themselves.
You mentioned Intel, AMD, and NVIDIA from a GPU perspective. What about things like Freedreno? Would that still be able to leverage the whole SYCL?
Yeah, so the idea for the ARM drivers as well, one of the big contributors to some of the OpenCL IR code in Mesa is Robert Clark, who did the Freedreno driver. So he's working on it because he needs to have a CL solution for Freedreno. So we are planning on Freedreno. I think there's possibility for of the other the Panfrost, OpenMali stuff, and those guys, once they've got a baseline up and running, that because they are building a Gallium driver, and once you've built the Gallium driver, you just have to validate that it can run. So,
any more questions at all?
So Intel's also going to be building in FPGAs integrated onto the processor. So is that team also talking to the GPU
They're
unit
still
in Intel?
firmly in the we don't want to tell you how to build FPGA bitstream camp, unfortunately, which means any stack they produce is probably they could share the top part of this stack, but the bottom part would be proprietary only. They have an execution environment, but that's only to put the FPGA stream onto the FPGA. It doesn't actually help you building it. So I think FPGAs are going to take a bit more work to bring into the fold.
What about OpenCL ES? Does that fit in there?
Not really. OpenGL, I hesitate to say on camera what I currently thinking of OpenGL is, but
I'm sorry, OpenCL ES.
OpenCL, yes. No, it's pretty much just OpenCL. There isn't really an embedded variant of OpenCL. There's a newer, OpenCL have realized some of their mistakes and are doing an OpenCL project to try and make the API. One of the big problems I think with OpenCL, which I have said on camera before, is that they took a bit of a kitchen sink approach, and anyone that wanted any feature got it thrown into the standard. And the hardware was coming out 2 or 3 years later, and it was like, well, has anyone ever implemented all that stuff you put in the standard? And it's like, oh no, we just thought hard about it. And it's like, okay. So now we're starting to hit those features, and we're realizing we've put things are in the standard nobody can implement, or they're not going to get implemented properly. So I think there's going to be a bit of a push. But from my point of view, I would rather that things would concentrate on the higher level SYCL language and leave the like SYCL has OpenCL interop, but I'd rather nobody went near that. I don't think it's the best plan. Yeah, things like Eigen and TensorFlow can be ported to SYCL. TensorFlow has already been ported to one of the prelim SYCL releases, but the current TensorFlow master is not compatible with the current release standard. And like I've had one patch to TensorFlow for add tree line, include headers, just like waiting for about 6 months. So I'm not really sure. That's one of my next focal points is to try and gather everyone that's doing their own TensorFlow ports and trying to pull them into one place and start getting upstream to care about it, because so far upstream just doesn't have the care factor.
I have one more. When you're doing this preliminary work, are you working on AMD or Intel? You're clearly not working on Nouveau.
No, I've been mostly doing it on one of my AMD machines, but I have done some on Intel. I actually took a binary I built in May and pulled it onto my laptop in like October, November last year and executed it. So it definitely works, but but mostly that was just because the Intel people just had all the bits in the right place, and I merged them together. And it was like, oh look, I can execute things.
So if people wanted to join in, which card would you recommend them working on?
I'd probably be targeting an AMD at this stage, but Intel's not far away. You can build an Intel stack that can do this, and some engineers are actually working on pieces of it, so it's definitely possible.
Okay, I'd ask you all to show your appreciation today for